So I think that is all I wanted to say about analysis. Now I'm gonna do a quick example of generative geometry, which is sort of what Grasshopper is known for. And I'm gonna do this just to show you an example of surface treatment. So this is gonna relate more to the second part of your assignment, where you're really asked to think about how a surface treatment of your form can influence its, can affect its performance. And for that, I'm gonna work with my original form. So I have my original form here. And I just want to go in and hide everything else. So I just have my form visible. And what I want to do as an example is create a system of panels on this form that I can, just in the most basic way possible, rotate to allow air and sun into this object. Okay? This is going to be just like a really quick paneling example, but you guys can basically adapt it to any other kind of surface treatment. So there's a lot of different ways to do paneling. Paneling is one of these traditional ways that like first got taken up with the Grasshopper. Like instantly people found use in Grasshopper, like paneling the complex forms. This is like why a lot of the examples you see are like these crazy forms that have these like super rational paneling systems. But yeah, so it's really good at that. There's a number of ways to do it. The way I really like to do it is by actually converting from a surface into a mesh, because a mesh inherently is composed of a lot of panels, right? A lot of different parts. And meshing is a quick way to work paneling. The geometry has to be right, but anyway, there's a lot of different ways to do it. You should experiment on your own. So I can take my surface here, and the first thing I'm going to do is if you double click and start typing mesh, there are a few options. One option to convert a surface into a mesh, and I won't get into the difference between surface and meshes. That's more like a bit of Rhino question, and you can explore that on your own. They're kind of fundamentally different geometry systems that are both supported in Rhino. There's different reasons you'd use NURB surfaces and meshes, but that's a topic for a whole nother discussion. So for now, I'm just going to tell you that that's what we want to do. And here we have a surface. One way to convert to a mesh is you just pass the surface into a mesh component. It'll do the conversion for you. It's probably going to give you not the thing you want. It's going to apply some kind of default algorithm and give you a mesh. But if you think of it as the building, you probably don't want these to be your panels. Like it's mixed between triangles and squares. It's pretty messy. There's also another component called mesh brep, which will take a brep and convert it to a mesh, same thing. But here it'll allow you to set some settings, some options. And these are similar options to what you would find in Rhino when you're converting from surfaces to meshes. So that's another option, a little bit more control. The way I really like to do this is the third way, which is mesh surface. And this gives you a little bit more control, but it also requires that you're working with a well-defined NURB surface that has some U and V information, and the U and V information is relevant to your surface. So if you have some very complicated, trimmed, and joined poly surface, it won't work as well. In my case, this is just a smooth surface going around. So you can see there's some options here. The first is I can plug in a surface, and it'll give me the default here. See, it's a very rough approximation. And how it's working is it's giving me an approximate mesh based on a resolution in the U and V coordinates. So I can actually tell it how many panels or mesh faces I want in both directions of the surface. Okay? And these I can control. So I'm going to set these up as sliders. I'm going to create one slider to control the U number. And I'm going to copy and paste that slider to control the V number. So now I have like dynamic control over how the paneling is working. I really like this way because you can really control the size and the kind of resolution of your panels. All right, And you run into some problems, like maybe this isn't what you want. And there's other more advanced tools to handle these kind of things, but for now this is pretty good. Okay, so now I have a meshed version of my surface. Here's the mesh in here. The next thing I want to do is I want to actually explode this mesh into its separate faces, because what I want is I want each of these panels as a separate object that then I can start to play with as a panel. Okay, so we have a mesh. We use the mesh to basically get a rationalized version of our surface in panels. Now we're going to convert it back into a surface. Okay, so we can reconstruct these surfaces. So basically what's happening here is I've deconstructed the mesh, and it's giving me all the faces, and then I have this other component called deconstruct face, which gives me all the indices of the vertices of those faces. It's a little bit complicated, and it has to do with how meshes work. It's a weird kind of data representation problem. But now if I have all the vertices, this is telling me for each face where to find the right vertex for the four vertices of each face. So now I can use a node called list item. So any data that's kind of multiple pieces of data, so you see here we have 105, it's a list, right? So if we go here, we want the vertices. There is 128 vertices in our mesh. We can actually go in and get specific pieces of that data, and this is what we want. So we want the specific vertices coming from this list. Okay, so there's different nodes, there's different tools for working with lists in Grasshopper, and most of them are found under sets, list. And there's all these different ways to do it. And what we're going to use is this one called list item. And this will basically take a list, for instance, the vertices, and then allow us to give an index of the thing that we want from that list. So you can think of all these vertices in the bag. We're coming in and pulling out specific vertices that we're looking for. And those indices are going to come from this node, which is telling us for each face what are the nodes, what's the position in the list of vertices that we want. So this is going to be a collection of points, and we just want to duplicate this 4 times. The list will be the same. We just want to connect the indices to the A, B, C, D outputs. So can you see that? We have one item node for each of these indices, and they're all being pulled from this vertex list. Okay, so now what we have is 4 collections of vertex points, and we just want to reconnect those. So we basically want to take the first one from here, 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 define that as a surface, and so on and so forth for 105 times. So let's see if this actually works. I'm going to use a component called surface 4-point surface, which conveniently will input A, B, C, D points and connect them into a quad surface, kind of a polygon. So if I connect all those in here, basically it'll go through each list and take the first item from each list and recompose those surfaces. So what I get out is 105 surfaces. Let me just hide this stuff. So now I have the panels as individual surfaces.